So thanks very much for the invitation. It's great to be here again. The four-color theorem, the statement of the theorem is 4 colors suffice. Here the plane is divided into regions, regions separated by black edges in the picture. The statement is that we can always color the regions using 4 colors so that adjacent regions adjacent along an edge have different colors. Here the colors are red, green, blue, and gray. And I've chosen to color also the outside region, or this is on the 2-sphere, and we've treated all regions equally. So this was proved with computer assistance by Appel and Harkin in 1976. A proof which took a while to see a final stable version. Robertson, Sanders, Seymour, and Thomas sort of reworked the proof, started again from scratch, produced a more efficient version of a proof also with similar computer assistance, a proof that was eventually sufficiently organized that it could be worked into the formal language Coq for a computer-verified proof of the computer-dependent parts of the argument. But we're still looking for a human-readable proof of the four-color theorem. The amount of computer time, of course, has dropped dramatically as computers have got a lot faster since 1976, not to mention improvements in the proof. But there's nothing here close to what we could read and check ourselves. So I just want to formalize the statement for our purposes a little more. The regions in the plane are separated by the edges of a graph, a planar graph I'll call K. Not every planar graph is legitimate when we're considering the four-color theorem, because our edges are to separate regions. So the regions either side of a given edge must be 2 distinct regions in the situation of the four-color theorem. So the sort of graph we're talking about has no bridges. This is a picture of what a bridge is for a graph. It's an edge which, the removal of which will separate the graph into 2 components, or equivalently, it's an edge such that the regions on either side of the edge are actually the same region. So we want only bridgeless graphs when we're talking about the four-color theorem. The other point about these graphs is that we may assume our graphs are trivalent. That is, that every vertex has valence 3. In the map of the United States, there's a unique point like so, where 4 states meet at a corner. If we enlarge this state, which I think is Arizona, and shrunk its neighbor, which I think is New Mexico, we actually make the job of four-coloring the map only harder, because now Arizona and Colorado, Utah, I don't know, they now have a common border, which they didn't used to. So if we can color the the new map, we could have colored the old one also. So for the sake of the four-color theorem, we can consider graphs without bridges and where every vertex is trivalent. So going back to 19th century, Peter Guthrie Tate thought about the four-color theorem and happened upon the following idea. So we now call this a Tate coloring. A Tate coloring is a coloring of the edges of a graph with 3 colors. So it's a trivalent graph. We use red, green, and blue here. And to be a Tate coloring, at every vertex, all 3 colors must appear. So at every trivalent vertex, red, green, and blue all appear. The question of whether you can Tate color a planar trivalent graph is exactly equivalent to the question of whether you can four-color the regions of the graph. In fact, by coincidence, if this screen went up, or if you're sitting on that side of the room, you can see that already stated from, I think, this morning's seminar on rather slightly different topic, but behind the screen here. But this is an elementary fact. You can find it written down in Tate's collected works, and he writes down there what is essentially the multiplication table for the Klein 4 group. So the rule here, given, you can go both directions, but given, say, a coloring of the edges, if you want to find the corresponding coloring of the regions, the rule is you start anywhere you like and pick, say, color gray. You think of the 4 colors as belonging to the elements of the Klein 4 group. And starting from the outside, you just work your way in region at a time. And every time you cross an edge, the edges having been previously colored, every time you cross an edge, you change your choice of region color according to the multiplication table of the Klein 4 group. So if here you've got a green region, you cross a blue edge, green times blue is red in the Klein 4 group, you color the next region red. And the fact that this is consistent, the fact that it doesn't matter which path you choose as you wind in, just depends on the fact that at every vertex, the 3 edges are colored A, B, C, and in the Klein 4 group, A times B times C is 1. So that's how you go from edge colorings to region colorings, 3 colorings of the edges to 4 colorings of the region, and vice versa. So this is what Tate observed, that the FourColor theorem is equivalent to the statement that you can Tate color, you can 3 color the edges of every bridgeless trivalent planar graph. And there's a graph illustrating that. What's interesting about this, we've now, the notion of a Tate coloring of the edges doesn't depend on planarity of the graph. We can now forget about the plane, and we can just think about the abstract graph, planar or not, and consider the question of Tate coloring its edges. So for the purpose of this talk, Tate of K is the number of Tate colorings of a graph, not necessarily a planar graph, but a trivalent graph K. So here's some examples which also illustrate what I mean by a graph. Our graphs are topologists' graphs. They're just topological spaces which are locally homomorphic either to an arc or a Y. Our graphs don't have to have any vertices, therefore this is a graph with no vertices, it's just a single unknotted circle. And when I say Tate colorings and count them, I can color the circle 3 different colors, red, green, and blue. And those are all different colorings from my point of view. So I'll say that the number of Tate colorings of this graph is 3. This graph has 3 edges. I've got to color them 3 different colors. I can permute the 3 colors, 3 factors, the number of Tate colorings for that graph, which has 2 vertices and 3 edges. The next one is the edges of a tetrahedron, that circle with the symbol in the middle. Again, 3 factorial is 6 is the number of Tate colorings for that graph. Essentially unique way up to permuting the colors to color this with 3 colors. This one, important example, does not have any Tate colorings. Just having a loop immediately tells you there's no Tate colorings because the incident edges here have to have different colors, but it's the same edge. But just going a little bit beyond that, it's an elementary argument that whenever there's a bridge, there can't be any Tate colorings. So this sort of graph has no Tate colorings. But then that sort of graph is not the sort of graph which we're concerned with if we're thinking about the FourColor theorem. In the world of topology, coming out of quantum algebra and stuff, trivalent graphs play a role. They often are referred to as webs in this context. The exact terminology varies a little bit from author to author, but for us, very simply, a web I'm going to use to mean a trivalent graph K, but now embedded in something 3-dimensional, a 3-manifold Y. So we're moving from abstract graphs or graphs drawn in the plane to graphs embedded in 3 space. This is a key move. Most of the time, the 3 manifold will just be R3. I'll talk about spatial webs for a case of a graph embedded in 3 space. So these are examples of what we mean by spatial webs. Most of those are visibly sort of planar. They're drawn as if they lie already in R2. And we've seen them before. 2 of them are not. This guy is 2 linked circles, the Hopf-link, joined by a single edge. And as an abstract graph, the graph here is the same as this one. But it's embedded in 3 space in a quite different way. Similarly, this is a trefoil knot, and it's just the underlying topological space. The underlying graph is still the same as that of the circle, but it's, again, the embedding is different. So the embedding is an important part of the data for this spatial web. When we're looking at bridges, we ought to distinguish ones which are sort of manifest in the embedding in 3 space and those which aren't. The word I'm using for this, for better or worse, is embedded bridge. So the difference between these 2 guys, although the underlying graph is the same manifold, same topological space embedded in 2 different ways, here the bridge is such that there's an actual 2 sphere in 3 space which transversely intersects this edge and hits it in just 1 point. It has this sort of topological 3-dimensional reducibility. That guy there, which is abstractly a bridge from the graph theory point of view, is not from the 3-dimensional point of view the same thing at all, because there's no 2 sphere which separates the graph into 2 pieces, cutting that edge. So I'll call this an embedded bridge, and as opposed to that picture over there. So what we're going to do is define an invariant of spatial webs. For every spatial web, we're going to associate to it a vector space over F, which is always the field of 2 elements. I'll call it J sharp of K in my notation. It's the instanton homology of the web K. It's a finite-dimensional vector space over the field of 2 elements. So I'll outline the definition, and then after some other discussion, I will close this talk with an outline of the following result, which is the main result we have about this instanton homology. So the main result about the instanton homology of a spatial web is that it's basically always non-zero, the exceptions being if there's an embedded bridge. So it's a non-trivial vector space, except in the cases we understand very well. And because it says something is non-zero, this is, for us, a non-vanishing theorem. It's a non-vanishing theorem for the instanton homology that we will define. So alongside this non-vanishing theorem, which is a theorem, there's a conjecture. And the conjecture is that in the special case that the spatial web is planar, by which I mean it really sits in R2. I don't mean it's abstractly isomorphic to a planar graph. It actually sits in R2, in R3 as a spatial web. In that case, this 2-dimensional, this Z-mod 2 vector space, this instant homology J sharp, its dimension is equal to the number of Tate colorings of the graph K. And this a little bit in my talk, perhaps a little bit more in Tom's talk afterwards, this conjecture will be elaborated on to see why it might be connected with some reasonable mathematics. But for now, the main point for me is the implication of this conjecture. 2 slides ago, we saw a non-vanishing theorem. We said that the dimension of J sharp was non-zero. So if the conjecture is also true, we learned that the number of Tate colorings is non-zero, with the exception of graphs with bridges, the case we expect to be exceptional in this. So this would imply the FourColor theorem. It implies that the number of Tate colorings is non-zero for any bridgeless planar trivalent graph. So just some simplest examples before I even tell you much more about what J sharp, the instant non-homology, actually is. The very simplest webs that we saw in the previous tables, the number of Tate colorings of the unknotted circle is 3, and the dimension of J sharp is 3, the instant non-homology. The next guy is the tetrahedron graph, and number of Tate colorings is 6, and the dimension of the instant homology is 6. There are no Tate colorings of this graph with an embedded bridge, and this is also the exception to the non-vanishing theorem. The dimension of J sharp in this case is 0. But this is an interesting thing to observe, that the Tate colorings is a property of the abstract graph. These two things are abstractly the same graph. Neither of them have any Tate colorings. But this graph does not have an embedded bridge. The non-vanishing theorem asserts that the instant homology is non-zero for this guy. That's J sharp. And indeed, the dimension of J sharp in this case is non-zero. It's equal to 4. You will notice that all the graphs here are rather simple. Here's another example where the embedding in free space is important. There's a unknotted circle or a knotted circle. It's the same circle abstractly, one Tate coloring up to choice, 3 Tate colorings where we're counting them in both cases. But the dimension of the instant homology is strictly larger in this case. It's 7 as opposed to 3 in the planar case. This is the one skeleton of a cube. The number of Tate colorings is 24, and so is the dimension of instant homology. But we're not very good at calculating, and as soon as you get to a graph which is remotely interesting from the point of view of coloring graphs, this is the one skeleton of the dodecahedron drawn in a rather non-visual way. What it is. It has 60 Tate colorings, but already in this case we can't compute the instant homology J sharp. We don't know what its dimension is. We have some upper and lower bounds. The lower bound we have is 58, and best upper bound at the moment is 68. The sort of direct approach that we're taking to try and understand the dodecahedron case might pan out. It might be feasible to prove that the answer is 60 by just improving the work that we did to get the 68, for example. But we don't know. And this is there to illustrate the fact that directly computing this instant homology from the definition is not something we can do.
Do you see any reason why it should be divisible by 6?
Last time I gave this talk, I had exactly the same question at almost the same point. And no, there's no reason why I see that it should be divisible by 6 even. Right? I mean, because any argument that says it's divisible by 6 would have to use planarity, as we've seen in the examples, and we don't really know how to use planarity. So I want to tell you something about how the instant non-homology is defined. And the starting point, well, one way of motivating the starting point is to think again about Tate colorings If you think of your graph, even think of a planar graph as sitting inside 3 space, you may think of its complement in 3 space or in the 3 sphere. And as you would do in a topology course for a knot or a link, you can consider the fundamental group of the complement. So many knot invariants might start from the fundamental group of the complement of a knot. A Tate coloring for a spatial web K is exactly the same thing as a homomorphism from this group, the fundamental group of the complement, to the Klein-4 group, with the restriction that it map meridians to elements of order 2. So in a Tate coloring, we're just labeling the edges by either A, B, or C. What would we be doing if we're looking for a representation of the fundamental group pi, a map to the Klein-4 group? That the fundamental group is generated by loops like this, which I'm calling meridians. They start at the base point, they walk to an edge, they loop around the edge, and they walk back to the base point. And if I'm asking that each one of these meridian loops maps to an element, yeah, and the homomorphism is non-trivial because I'm asking that the meridians map to elements of order 2, not well, I mean strictly order 2, and not that their square is 1.
That is equivalent to the homomorphism being non-trivial.
It's not quite the same in general. It is in this for this particular graph, I believe. So in this example, I have to pick an element of the Klein-4 group for each of the meridional loops. That's the same as picking a color. In this fundamental group, meridional loops correspond to 3 edges incident on a given vertex. Their product is 1, and that's reflecting the condition that the 3 colors, the Tate coloring conditions that the 3 colors at each vertex be 3 distinct colors. That's the only way that you can have the product be 1. So the relation in pi that the 3 meridional loops multiply to 1 is exactly the Tate coloring condition. Things are a little simpler here because the Klein-4 group is abelian. We don't really have to think too much about the order in which we multiply these guys, particularly as they're elements of order 2. We don't even need an orientation. This is just the sort of Z mod 2 homology of the complement of the graph that's really in play here. Once we've thought of homomorphisms to the Klein-4 group, and being gauge theorists at heart, we want to replace the Klein-4 group by the larger group of all rotations of 3 space. I want to embed the Klein-4 group as the rotations about 3 standard axes, the coordinate axes in R3, 3 orthogonal elements of order 2, and rather than just these particular elements of order 2, I now want to enlarge my range and consider all the elements of order 2 in SO3. The 180-degree rotations about arbitrary axes in 3 space. And now we can think about something which we might regard as a generalization of a Tate coloring, a loosening of the idea. We take the same group, the fundamental group of the complement, pi, and I'm defining now a variety R sharp of K, this representation variety, it's the space of all homomorphisms from the group pi, not to the Klein-4 group anymore, but to SO3, but still with the restriction that the meridians map to elements of order 2. So inside this representation variety sit the Tate colorings, those where the rotations are just about the 3-coordinate axes. But now my game is more general. For every edge, every corresponding meridional loop, I have to pick an axis in 3 space. And I've still got the constraint that at each vertex, the corresponding 180-degree rotations must multiply to 1, which becomes the condition that the corresponding 3 axes in 3 space must be mutually orthogonal. For a very simple graph like this, the SO3, the homomorphisms to SO3, which satisfy this condition, they're really the same as the ones to the Klein-4 group, but just kind of rotated around by SO3. For more complicated graphs, there starts to be a significant difference. So there's a standard plan here, which sort of goes back to Andres Fleur's definition of instanton homology. This representation variety, our plan is to view it as the critical points of a functional, a Chern-Simons functional on a space of connections. We'll then perturb this functional so that it satisfies more Smale conditions, and then we'll be able to define the instanton homology. It'll be defined as the Morse homology of this functional. What that means is that we'll perturb so the critical points are a finite set, and we'll define the instanton homology as the homology of a complex. The generators of the complex, the basis for the complex, will be indexed by the critical points, and the boundary map in the complex, its matrix entries will count flow lines. The Morse trajectories will be flow lines of the Chern-Simons functional. These observation that goes back into Fleur's original Fleur homology, these flow lines could be interpreted as Yang-Mills instantons, which eventually is why we can't directly compute them. In the very simplest examples, what this is going to turn out to be, the very simplest examples, the representation variety is already a smooth manifold, and J sharp of K turns out, it doesn't have to be, but it does in the simplest cases, it turns out just to be the ordinary homology with Z mod 2 coefficients of that representation variety. So that's what happens in these the examples you can see here. Here the fundamental group of the complement is just Z. We're mapping Z to SO3, mapping a generator to an element of order 2, i.e. an axis in 3 space. So the homomorphisms, the representation are just the set of axes in 3 space, which is RP2. It turns out that the instanton homology is just the ordinary homology of RP2, which with Z mod 2 coefficients is 3-dimensional. This guy, the pi maps to the group, the fundamental group of the complement pi maps to SO3, its image there sitting as the Klein-4 group itself, and the representation variety K just parameterizes all the Klein-4 groups inside SO3. And that's really this quotient here is a real flag manifold, unoriented flags in real 3 space, and that's a space with 6-dimensional homology over Z mod 2. And again, 6 is also the dimension of J sharp. It's also equal to the number of Tate colorings in this very simple case. If there's an embedded bridge, this representation variety is always empty. There's a meridional loop corresponding to this edge, which we require to map to an element of order 2, but that meridional loop is null homotopic, so there can't be any such representation. The representation variety is empty in this case. J sharp is 0. For this guy, you can directly compute there's an essentially unique homomorphism to SO3, whose image is a copy of dihedral group of order 8. It has a stabilizer of order 2. This quotient is a lens space with a cyclic of order 4 fundamental group. Its ordinary homology has rank 4, which again happens to be the dimension of J sharp in this very simple case. I want to give a few more details about how J sharp is constructed. So the first point is when we look at say representations of a group, what we're normally thinking of looking at is representations up to conjugacy. We look at isomorphism classes of representations of a group. We don't normally look at homomorphisms themselves. So rather than this guy I've called R sharp of K, just the raw homomorphisms to SO3, what one would normally think first of looking at is the homomorphisms divided by the action of conjugation, divided by SO3 acting on the target space by conjugation. This we can reinterpret then as flat SO3 connections up to isomorphism, flat SO3 connections on the complement of the embedded web. Now, apart from the fact that these two guys are just different, one problem that arises for gauge theorists when looking at this guy is that we're now looking at a quotient space where some of the points we're interested in have non-trivial stabilizer. If the image in SO3 is, for example, the Klein-4 group or sits inside a dihedral group, there'll be some non-trivial stabilizer. And to make a gauge theory that we can actually define and work with, we need to consider a situation where there are no stabilizers. So that this will start us on a road which gets us back to this guy. But the device to do this while staying in the world of SO3 connections is the following. So we're going to introduce extra data in 2 steps. And one of the bits of extra data we're going to bring in is, I'll call it a marking. Given a graph K like this, we can consider R sharp of K, this representation value. In this particular example, I said it was a copy of SO3 divided by the Klein-4 group. This is the flag manifold. This would have non-trivial stabilizer, the Klein-4 group, if I considered it divided by, if I divided by SO3 acting by conjugation. Inside SU2, the lift of the Klein-4 group has no stabilizer. If I take the inverse image of the Klein-4 group in SU2, I get the group of order 8, which has no stabilizer in SU2. So what we're going to do is introduce an open set, I'll call it mu, which will typically be the neighborhood of some vertex of the graph. And instead of just SO3 connections, we'll look at SO3 connections together with a lift to SU2 on that open set. I'll call these marked connections. A marked connection, typically in this situation, will have no stabilizer. The stabilizer there will be isomorphisms between two of these gadgets. If an isomorphism exists, the isomorphism is unique. That's a better way of saying it. So in this example, the representation variety divided by the full isomorphisms is just a single point, but a point with no automorphisms now. The other part of this marking game is to introduce, somewhat ad hoc, an extra bit of graph which I'll take to be a theta. So given a graph K, I'm going to throw in an extra theta graph. I'm calling it a theta graph because when it's drawn on its side, it's a theta, together with a marking of one of the vertices. So the bit that I've introduced there, that I've thrown in this gadget, which admits a unique marked connection with no automorphisms. And the effect of that is just to sort of undo the fact that we've divided by SO3. So the effect is that the original R sharp of K, the thing I defined without dividing by SO3, can be identified exactly with the marked representation variety divided by the full automorphisms of this new graph K with the theta and with the marking. So that extra theta and that little open set mu, I want to think of it as sitting far away, and it's sort of effectively giving us a base point where the connections are, as it were, sort of trivialized. Yeah?
Is all this happening in S3 or R3?
At the moment, it's just on the transparency, but it'll be in S3 very shortly, yes.
So the theta is a lot like, morally speaking, it's a lot like being on R3 in such.
Yeah, I mean, it would be nice to do the gauge theory with some sort of boundary condition at infinity. Technically, we don't know how to do that, so we do this instead. Yeah. The other technical move here is that we don't really know how to do gauge theory very well on the complement of a graph in 3 space. For this reason, it's very handy to pass, as is sort of fairly standard in other aspects of 3-manifold topology, pass from this sort of embedded web or graph in a 3-manifold to thinking of an orbifold geometry, where the web now represents the points with non-trivial stabilizer in the orbifold. So given a little bit of edge here, I want to reinterpret that as a patch in the orbifold where the chart would be the standard 3-ball divided by an involution. The involution having stabilizer, the arc running through the middle of the 3-ball. If I divide the 3-ball by the Klein 4 group acting in the standard way, the 3 coordinate axes become 3 rays fused at the origin. The quotient, the 3-dimensional quotient is topologically a 3-ball, but the 3 coordinate axes, the points with non-trivial stabilizer, become these 3 rays. So that's how I interpret the vertices of the web. In that way, given a graph with this additional theta graph thrown in, sitting inside S3, I pass to a 3-dimensional orbifold, which I'll, for the moment, call Y. Yes, that's what it looks like. The Klein, the 4-ball divided by the Klein 4 group is yeah. So the 3-ball divided by the Klein 4 group is the 3-ball, and the points with non-trivial stabilizer in the 3-ball start off as the 3 coordinate axes in 3 space, and in the quotient they become these 3 half lines coming out of the origin. At least as a topological space. So mostly from now on, defining J sharp of K is sort of standard technique in sort of Flow homology. What we've done is we've taken K, we've added a theta graph. We've got a situation where we've got a space of connections. None of the interesting connections have any stabilizer. From that, we've built an orbifold, Y, and we're just going to do, we're going to regard R sharp of K now as just a space of flat orbifold connections on this orbifold Y. These will be the critical points of the orbifold Chern-Simons functional, In general, in 3 dimensions, the Chern-Simons functional has critical points, which are the flat connections. It's true on orbifolds also. And we know how to define the Morse homology in most situations for a Chern-Simons functional, and that's what Fleur originally did. In our case, in this setup, it's going to define our Instanton homology K. As I said, its generators are the critical points. Its boundary map counts instantons, which are going to be solutions of the Yang-Mills equations on R times Y. There are a couple of points in which this particular Fleur homology differs from other instanton homologies that are otherwise very similar. So there are 2 points. The first is in the proof that one has d squared equals 0. So d, remember, the differential is defined by counting flow lines between critical points. And there's a standard argument in Morse homology for proving that d squared is 0. And it relies on the fact that if you look at the gradient trajectories between 2 points whose index differs by 2, after dividing by translations, you'll have a 1-parameter family of these, and the endpoints, the non-compactness in that family is exactly due to a gradient trajectory between say index 0 and 2 breaking up as a composite trajectory between an intermediate index 1 critical point. This requires some compactness result, which in Instanton homology comes down to Uhlenbeck's compactness result for the Yang-Mills instantons. In this orbifold case, there's still an Uhlenbeck type theorem, but the dimension counting which it leads to is different, because there's a type of bubbling which can happen at the vertices of the web. And unlike the sort of familiar drop in dimension by 8, which would happen with sort of instantons on the force sphere, what happens here is a drop of dimension by 2, and that interferes with the proof that d squared is 0, this bubbling at the vertices. So a 1-manifold which you want to be compact modulo broken trajectories actually has some extra non-compactness, some extra ends. But if you analyze the gluing picture, the Klein 4 group plays an interesting role. And the number of extra ends you come up with is, they come in groups of 4. So if you work in characteristic 2, then you still prove that d squared is 0. And as far as we know, it's still necessary. I mean, I think that's probably an essential thing which we can't get around. I'm not sure, but from what we see, you actually can't define this thing over the integers. It needs to be done over z mod 2.
Could you do it much further?
Well, that's if you were brave, you might think about that. Yeah, as soon as you go to anything other than z mod 2, you also need at least a bit of a sign. I mean, in z mod 4, you need to distinguish the 2 generators, and we have a problem, I think, with that as well. The other thing about this homology, I mean, I talk about it as a homology and a complex, but when you say homology, you tend to think it's z-graded. This isn't z-graded. It's not even z mod 2 graded if the graph isn't bipartite. It's really just a group with an operator d on it with d squared equals 0. And again, that lack of, well, the existence of only a z mod 2 grading in the bipartite case is related to that bubbling phenomenon. In the non-bipartite case, the fact that grading is even broken for z mod 2 is a little more subtle. I want to say a few remarks about this conjecture before turning to the non-vanishing theorem. The conjecture that the dimension of this homology group is equal to the number of Tate colorings for planar webs. So the first thing is that this is not equivalent to the FourColor theorem. This isn't a reformulation of the FourColor theorem as another hard question. It implies the FourColor theorem, but it's a conjecture. And because it's a conjecture, not a theorem, and because it's not equivalent to the Appel-Harkin theorem, it might be false. But another thing to say about this conjecture thought, I mean, if this conjecture is true, it is reasonable to try and prove it, in the sense that if you showed someone this conjecture and didn't tell them about the FourColor theorem, I mean, it sits there in a whole lot of mathematics. It's not just some thing you look at and say, no way. There's lots of things you might try, and Tom and I have tried a few. The other thing is that write it down on a small piece of paper and give it to me after. No, yeah, I mean, a bordered theory would be kind of the obvious thing to try and do to really, I mean, if you were really being macho about this, then probably a bordered theory would be an excellent thing to try and develop. If you want the list of the things that we've tried, we can talk afterwards. Yes.
Is J-sharp, is that an interpretation of the suture for homology?
Yes, actually, that'll almost, but not really. I'll come to that later if I don't run out of time. Yeah. The other thing about this conjecture, I mean, we don't make this conjecture just because it implies the FourColor theorem. It's not a sort of, that's not quite where it comes from. It would be the first thing you would guess if you were us and you came across J-sharp. There are other similar things which are true. If you replace SO3 by SU3 with some very slight modifications, you can repeat everything I've said, and you'll define a different instant homology. And its dimension will count the number of Tate colorings. Unfortunately, though, for that SU3 version, you lose the non-vanishing theorem. No, it's actually no. So the non-vanishing theorem is definitely false for the SU3 theory. I mean, in fact, the SU theory is rather dull, and it doesn't really distinguish the embedding in free space. It really is the number of Tate colorings even for a non-planar graph. So it's considerably duller than the SO3 case.
But what everything you lose the non-vanishing, I mean, it counts Tate coloring, so you cannot lose the non-vanishing.
Yes, you can, because I mean, it's yeah. Well, for planar, you can't lose it. But I mean, and the SO3 guy, we have a non-vanishing theorem, even for snarks embedded in free space. But the SU3 case will just give us 0 for those. It's less interesting. But slightly more generally than this, there's sort of family of similar questions, some more subtle than others. The very simplest of ones of which, and the SU3 is the simplest, we think we know how to prove. The more interesting ones, we don't know how to prove. For those who know what these things are, there's sort of Havanov-Rosansky homology, which also is an invariant of sometimes decorated trivalent graphs in R3. There are related instant homologies that you can define using other gauge groups, SUN. And their dimensions should count combinatorial things when the graphs are planar. The sort of combinatorial things they count are Moy states. Given a trivalent graph, a Moy state is a labeling, and to each edge you assign a finite set, lambda 1, lambda 2. The graphs are directed, and when a graph splits in this way, you must have a disjoint union, splitting up as its two union ands, or whatever the words are. For SUN, lambda I, the lambdas are subsets of 1 through n, and you specify their dimensions in advance. Yes.
So do we have Havanov-Rosansky for webs in S3 or just for knots?
Well, the status of the status of how well defined these things are for general sorts of labelings, I don't know. I mean, Havanov and Zansky's.
Like the SO3 case.
Sorry.
Like the SO3 case that you have Tate coloring. Do we have that in that? I guess what I'm asking is, do we have SL3 link homology, Kronheimer-Posanski link homology, or not for webs?
So I'm not quite sure who we is. So the
Set which includes you and Kronheimer-Posanski.
no. So I mean, as far as I know, the categorified quantum algebra invariant, which is supposed to count moist states for planar graphs, may not be well. I'm not sure if it's verified as well defined for embedded spatial graphs in general. There is an instant homology which is well defined. I don't know in all cases that the instant homology does count moist states for planar graphs. But without getting into specifics, these are sort of other things to convince you that the conjecture isn't isolated. It's part of a family of conjectures which makes sense. So I wanted to finish by talking about the non-vanishing theorem, which interesting because its proof is deep and in many ways non-trivial, which is sort of encouraging because we're kind of hoping that it might have something to do with proving eventually perhaps a difficult theorem. So if the proof of the non-vanishing theorem were very easy, I wouldn't have much faith in the conjecture, but my confidence in the conjecture grows the harder the proof of the non-vanishing theorem seems, sort of conservation of difficulty. So there are several steps here, and the first is to pass away from SO3 to SU2. I talked about having a marking region where we insisted on a lift from SO3 to SU2 over that open set. I now want to extend that to the whole of the orbifold Y. So instead of J sharp, I've got a modified J sharp. I'll call it I sharp of K. It's enough. If we can show that I sharp of K, we'll still win because it's like a finite sheeted cover, iterated double cover of the. It maps onto only onto some components because not every SU3 thing will lift to SU2. But if I sharp of K is non-zero, then some component of the J sharp space has some iterated Z mod 2 cover with non-trivial homology. If a finite sheeted, if a Z mod 2 cover has non-trivial homology, then so does the base with Z mod 2 coefficients. So that non-vanishing of I sharp will be sufficient. So we can now forget about SO3. There's now a sort of topological move. We're going to, having spent so long talking about vertices and webs and graphs, we're just going to get back to something without any vertices. We're going to cut out a neighborhood of each of the vertices of the graph. So here's S3, or perhaps R3, and it contains this embedded web, either K or perhaps K together with a theta graph somewhere in the distance. We're going to remove a 3-ball from around each vertex by cutting along a 2-sphere. In my picture, it looks like there's a circle, a 1-sphere, but it's a 3-dimensional picture. Those are supposed to be 2 spheres meeting the web in 3 points each, where the vertices, where the edges come in incident to the vertices. So cut out those ball neighborhoods, and then
How does the orbifold
it becomes an element of order 4, yes. And that's
it's not the same orbifold.
well, you can say that what we're doing is we're actually looking at SO3 connections, but so if we fix an SO3 bundle and look at all the SO3 connections on it, then instead of dividing by all the SO3 automorphisms of the bundle, we're just dividing by those automorphisms which lift to automorphisms of the SU2 bundle. So if you like, the connections are still SO3 connections. It's just our notion of the isomorphisms which is slightly changed. There are an even number of vertices always. So we're now going to glue together these twice punctured spheres in pairs, or equivalently, because it's easier to draw on a slide, join them by a tube. That tube looks two-dimensional in the picture, but it's not an arc times a circle, it's an arc times the two-sphere. The dotted, this is a two-sphere, that's an arc times a two-sphere, identifying the two two-spheres together. And the vertices are gone, the edges come into those two spheres. Now I run the edges over from the one vertex to the other. They run over this new arc times S2. Simpler but harder to draw. You just identify this dotted circle with that one to create a new three-manifold. And there are some choices involved, how you glue up and how you pair up the vertices, but any old how you do it. You obtain a new manifold Z, not a very complicated three-manifold. It's a connect sum of S1 times S2s. And inside it is a link, L. It's what has become of the web, K, once all its vertices are gone.
The link depends on your choices?
Yeah, the link depends on our choices. I mean, we have to choose arbitrarily a pairing up of the vertices and which edges get mapped to which three. There's another step here, that there are no vertices anymore. The problem with characteristic 0 was to do with bubbling at the vertices. Once the vertices are gone, we can use characteristic 0 and we can pass to the rational field. And it'd be enough if we can show that the rational homology is now non-zero in the Morse complex. So we're gradually getting towards more and more familiar territory for us. And I think that's by the universal coefficient theorem. And if the rational homology is non-zero, it's a finite complex, then the Z mod 2 homology is non-zero by universal coefficients. At this point, it starts to become a little bit graded. Yes, I think it's now Z mod. I'm not sure if it's Z mod 2 or Z mod 4 graded, but it had some grading. Yeah. At this point, we pass from this link in Z to its complement, which I'll write as M. We remove a tubular neighborhood of the link L, which we want to regard as a sutured manifold in the sense of Gabai's sutured manifold theory. This gets back to earlier work that Tom and I did, extending the notion of instant homology from three manifolds to sutured three manifolds. The suturing is a decomposition of the boundary into two parts called positive and negative, plus and minus. The sutures, so-called, are the simple closed curves which separate on the boundary two manifold, the plus and the minus regions. In this case, what the sutures are going to be are just little meridional circles running around the meridional curves, meridional to the link that we've removed. There's a topological step here needed to move on with applying Gabai's techniques, which is to show that this link complement as a sutured manifold is what Gabai calls taut. This step is here. This is a step where we use that there is no embedded bridge. In fact, this sutured manifold is taut if and only if the original web has no embedded bridge. This is a picture of what we've done. We've started with a web in S3. We've passed to a link in a rather simple three-manifold. We've deleted a neighborhood of the link to get a new three-manifold with boundary M, and we put these sutures on the boundary. And then we prove, assuming no embedded bridge, that this is a taut sutured three-manifold. The last step in this is the previous work that Tom and I did, which shows that if a sutured manifold is taut, then its instant-on homology is non-zero. This was a theorem that was modeled on an earlier theorem by Andreas Juhas for Heegaard flow homology. And in both cases, the proof is the same. It depends on Gabai's sutured manifold hierarchies. A sutured manifold hierarchy is a sequence of cuttings, starting with a three-manifold with boundary, repeatedly cutting along genus minimizing surfaces, trying to reduce, in a rather subtle way, the complexity of the sutured manifold until eventually the sutured manifold is a product manifold, surface times an interval. And the proof of non-vanishing theorem, the proof of the non-vanishing theorem is to say that the trivial product guy has non-trivial homology, and then you just follow it back up the sutured manifold hierarchy to get non-vanishing theorem for the original sutured manifold. And this step is topologically interesting. And even if you start with a planar graph, this three-dimensional construction of Gabai's, this sutured manifold hierarchy, takes you, I think, into a very three-dimensional along genus minimizing surfaces, which, at least to us, are very non-obvious. And I think even for planar graphs, this is a very three-dimensional sort of theorem, this proof of the non-vanishing theorem. So, and the take-home message here, I think, is that if, in addition to this non-vanishing theorem, if the conjecture is true, leading to a proof of FourColorability, if that happened, through this non-vanishing theorem, the proof would rest on three-manifold techniques in an essential way, decomposition, normal surface theory stuff, Gabai's work in particular. And so somehow the take-home message here is that we are hoping that there's a proof of the FourColor theorem, where the sort of combinatorial heart of it, I mean, if you like, the sort of proof by induction on complexity somehow happens in this three-dimensional world of three-manifold decompositions. So it's very nice that the whole idea of three-manifold decompositions and normal surface theory is very much associated with Wolfgang Haken, not just the FourColor theorem, but this is other thing for which his name is sort of permanently embedded in the language of mathematics. So Tom will talk after tea, and we'll tell you a little bit more about J-sharp, its properties, and formal things which make it sit reasonably in its conjecture related to Tate couplings. And that's the end of the talk. Thank you.